And it started. Okay, thanks, good. So today we have one of our new postdocs, Dario, and so he did his PhD in Potsdam University, and he obtained that degree last year, so he's almost a second year postdoc now. He's in the astroseismology group of CONI, but he does not have an astroseismology background, so what he did for his PhD was to study clusters, and in particular, he studied the rotational activity of cool dwarf stars, and that's what his talk will be about today. So please, Dario, you have the floor.
Okay, thank you. Well, as Joris just said, my talk will be about my PhD topic, which was on rotation and the spin down of cool stars in open clusters. And the work was conducted in correlation with all of these people, in particular Sidney Barnes and Klaus Strassmayer, who were my PhD advisors. I was at the Leibniz Institute for Astrophysics in Potsdam and obtained my PhD from the University of Potsdam. So I will start pretty broad because the stars that I'm going to talk about are probably have like lower masses than some of the error bars of stars that you're working on. So you're working on high mass stars. So I will talk about cool stars, and a cool star is everything with an outer convection zone. Like here on the right, this image, this is the sun, or a sketch of the sun. And if they have like a radiative zone in the center, then we call them solar-like stars. There are cool stars which are completely convective. If you go down to low mass M dwarfs, then they're completely convective and then no longer solar-like, but they share a lot of things. Of course, giant stars have also outer convection zone, but here we're talking about main sequence stars, which means spectral type mid-F, like 0.3 solar masses, all the way down to the stellar boundary. It always depends on how far our clusters are away, how deep we can go into this regime of low mass M stars. So that's like not a fixed boundary over there, but for the F stars, there is. Then these stars have an active dynamo, so we're talking about magnetic fields, and they rotate. So everything that people like to neglect, magnetic fields, rotation, that's pretty important here. And there are, of course, many observables related to the magnetic field and rotation, and I will talk about them. Okay, brief intro into the magnetic field. Sketch of the dynamo. This is a simple alpha-omega dynamo. There are more complicated theories, but I guess for you to get an idea how the magnetic fields are created. So first we start with this nice poloidal field over here. Then these stars rotate, and they are not stiff rotators. They rotate differentially. That means that the magnetic field lines are dragged along with the plasma at different speeds. And you get this curled up field over here. And once you have this toroidal field like this. And then there is convection. So mass is coming from down, going up to the stellar surface, which also drags along the magnetic field lines. And that gives you these kind of wiggles in here. These things make loops, like here. And the nice thing about rotation in this thing is that you have a Coriolis force, which is like the opposite sign in different hemispheres. So independent of your initial field line direction, you always have the same polarity of these loops, which then allows you to create, again, a large-scale dipolar field. And you've noticed maybe that here, field lines are going from north to south. Here they were from south to north. So this is the reversal of the dipolar field that we know as the solar cycle. So from here to there, it takes the sun 11 years. So like the total cycle is actually 22 years. Okay, I will talk about spin down. So let's see how can these stars, which are of course in vacuum, kind of, lose their angular momentum. And this is where our magnetic field plays an important role. So, but first of all, why do we care about angular momentum? So we know from observations that angular momentum can change on the main sequence by 2 to 3 orders of magnitude. This is quite a large range. If you think of a main sequence star, we have temperature, mass, luminosity, all of this is more or less constant, and then you have this property that changes by some orders of magnitude. So how does it work? You have your star over here, then you have a stellar wind, which is charged particles, so basically protons and alpha particles. And you know, when you put a charged particle in a magnetic field, it will move along the field lines. So it goes like radially outwards if you're on the rotating reference frame, which means that there is some force applied to this particle. If there were no magnetic field, then the trajectory would be like this. And this force, of course, there's also a counter force, and then you have this co-rotation radius over here that gives you a lever arm. So each particle in the stellar wind is actually pulling a bit on the star and is breaking it. However, the rotation, as we saw, is also driving the dynamo. That means the rotation and the magnetic field regulate each other, because if you have a fast rotating star, you get a huge magnetic field, but that also means that you have here a longer lever arm, and so the spin down rate is much faster. So in the end, there's a regulation and all of these stars spin down. Short history of gyrochronology. You may have heard this term before. If not, I will introduce it to you. So just like in the late 60s, 70s, that people noticed that there was a correlation between age and rotation. And then there was this famous paper 50 years ago where the figure, so there's only one figure, 2 pages of this paper, well cited. And you can see here there are 3 things. So there's lithium, rotation, and calcium activity over age. And you can see that all of these decay. And Skumanich back then got this, so it's that the rotation is declining with the square root of time, or 1 over square root of time. Up today, if there are like updated values, we are still in the 0.5 something region, so it's a pretty good fit with 3 data points. On the theory side, it was worked out that the angular momentum loss is cubic with the angular velocity, which is pretty strong dependence, and you can, of course, get this tau to the 1/2 from this if you integrate it. And then we have the introduction of gyrochronology in the early 2000s. That was from Sidney Barnes, who expanded this to non-solar mass stars. So he basically looked at kind of all masses of cool stars and noticed that we can get an age just from a prescription of rotation period and mass. And this allows you to kind of measure ages of cool stars. Then there's also another thing that is stellar activity. We have magnetically driven activity in the outer atmosphere of the star. And we know that, or we know from observation, that fast rotating stars have a high activity, but the fastest rotators, their activity is independent of the rotation period. You will see in data soon how that looks like. But first, what kind of activity is there? So there's the photosphere, where we have star spots and active regions. Then there's a chromosphere. This is actually just this thin pinkish ring over here. This is why it's called chromosphere, because it's colorful. And this is line emission from H alpha and calcium. Calcium both in the UV and the infrared, and some other not that important lines. And in data, it looks like this. So you have like the emission from this line against the rotation period, normalized by the convective turnover time. This is called the Rossby number. It's basically a mass normalization of your rotation period, so that allows you to put all kind of stars, no matter if they have solar mass or half a solar mass, onto the same diagram. And then you get this nice correlation over here, so that slower rotating stars have a lower activity, while higher rotating stars have faster rotating stars have a higher activity. And then, of course, the corona here in scattered light, but from stars we can observe soft X-ray emission. And again, we have a similar correlation here. So this is now called the Rossby number. This is the X-ray luminosity normalized by the bolometric luminosity. And here we can actually see the fast rotating stars. Their level of activity is independent of rotation, and then you have this correlated regime down there. Another thing that I have to introduce are the terms of slow and fast rotators. So in young open clusters, you have two regimes of rotators. There is the fast rotating regime, and there's the slow rotating regime. And this is like the outcome of star formation. So you can ask about later if you're interested, but for the time being, we don't care. These stars are just there. They're first observed in the Pleiades, and was kind of immediately seen that they cannot spin down the same rate as the slow rotators, which was like the cubic dependence, because Pleiades, you may know, is 150 megayears old around, and these stars would have spun down in a shorter time frame than they are there at their age. So there is something going on, and so they were proposed that they only spin down linearly. But at some point, these stars just going from fast rotation to slow rotation. So what it means, in this diagram over here, that we call the color period diagram, so we have the color or stellar mass, high mass stars here, low mass stars there, so in color it's going this way. And again, the rotation period, fast rotators, slow rotators. Here the fast rotator sequence, this is a slow rotator sequence. At some point, these stars from down here are just going whoop up there. So in all the open clusters, they're all gone. You only have this one sequence. But we don't know why. There might be some field configuration changes, or it's just random, but we don't know why. So, I mean, we don't know even yet really know why they're there in the first place. Yeah, and so this is why we are looking into young open clusters as labs for stellar astrophysics. You have homogeneous samples in there. They share the age, they share the chemistry and space motion, so you can really find them from in front of the background stars. But you have a variety of stellar masses, and there are therefore ideal calibration targets. The key, however, is to use a well-defined membership. Otherwise, you get all kinds of stars in your sample and no real results. But luckily to Gaia, we have 3D space motions, we have multiband photometry, and so they can work this out. So, for example, this cluster over here, one of the clusters that I studied, NGC 3532, there are about 100,000 sources in this field. Maybe not on this image, but if you go deep enough, like to 20th magnitude, then there are 100,000 sources. But only about 1% of them are cluster members. For the bright stars, you can easily tell all of the bright stars are cluster members. But when you look at the color magnitude diagram, then down here at like 16th magnitude, it gets complicated because there are a lot of background stars. And you really have to fish out only these stars which belong to the open cluster. So that's something that I did. And then when you have these open clusters, you can put them in an age rank because you more or less know the age from isochrones. And then you can already see how this spin down looks like. So we have like Pleiades down here, talked about them before. And then there's the older Chrysope. Then NGC 6819 from the Kepler field. Some of you may know this cluster. And then there's M67, which is at solar age. Sun is over here in this diagram. So we really know how these stars spin down. And you may notice that lower mass stars, so stars over here, have a much higher range of periods than the higher mass stars. This is just because lower mass stars have deeper convection zones. But what is happening beyond solar age? Well, that's something that people are currently looking into. So maybe there's a weakening of the braking, so that stars are not spinning down anymore. And this is what was just published last year. So these are like all the old stars in the Kepler field, the colorful dots, that we can get astrosseismic ages and rotation periods for, and of course temperatures. And then there is this model in the background. So this is not observation in the background, the blue one, but the model. And you can see there's this pile up, and the model of the weakened braking is kind of explaining it. So maybe there's something that when the sun is getting older, it's kind of staying as a constant rotation rate. Maybe not. We don't know yet. Okay, but let's talk about what I did. So what kind of observations do we have to measure these rotation periods? We use light curves, and we use the star spot modulation in there. So this is how it looks. I had ground-based photometry, and you can kind of already see what this sinusoidal shape is in here. Of course, these are just the best light curves. A lot of them are much noisier. And I also use spectroscopy. For 3532, I initially got some spectroscopy to get radio velocity membership down to 19th magnitude. That's in the infrared triplet. And as I just said before, the infrared triplet is also kind of interesting for activity, and we'll come to them later again. So NGC 2516, this is the other cluster that I worked on. You can see it over here. It's kind of a southern twin of the Pleiades. And this is what the membership looks like. Okay, and here are my rotation periods for this cluster. And just for you to remember, this is what the diagram means. And like I added all of these filled data points. Previously, there were only those unfilled data points known. But what is interesting is, as I said, twin of the Pleiades. And when you look at the rotation, it is. So if I would not put it here like the color coding, you cannot tell which is the Pleiades, which is 2516. That means it first confirms the age of 2516. But there are more clusters of similar age, and all of them, as I've shown, have like the same rotation period distribution. So in the background, it's always 2516. And then the colorful ones are different clusters, so M35, the Pleiades, M50, and Blanco 1. And what that means is that the rotation period distributions are universal across open clusters. And of course, pretty much strengthens the foundation of gyrochronology, because it was always like implicit in there that all stars of the same age should have same rotation periods, but now we can actually show this by data that these stars actually do spin down like similarly. Before I also showed you the activity, and for 2516 there are a bunch of X-ray observations. And here you can see this diagram as I've showed you before. So this is the X-ray luminosity against the Rossby number, and here you can see again constant luminosity, and then there's pretty much a steep region over here. And again, same clusters as before, all of these clusters fall on the same track, which is pretty nice. Here on the left, that's the color period diagram, and the sizes are the actual X-ray fluxes of these stars. They can already see in here that the fastest rotator down here have actually the highest X-ray fluxes. So this is what you, when you just look at like the brightest stars in X-ray in an open cluster, you will find these stars. The colors are just from different observatories, so XMM and Chandra, if you're wondering. Okay, let's talk about 3532. That's the second cluster. 3532 was a poorly studied cluster, although it's a pretty rich cluster. As I said, like 1,000 members, which not many open clusters have. There are 7 confirmed white dwarfs. It's also like a large population for an open cluster. And from the white dwarf, there's actually like this pretty constrained age. But it's just in front of the galactic disk. So this is what scared people away to work on this cluster. As I said, I got multi-object spectroscopy. Plus, I also had some 400 additional radial velocities. So I was able to get 660 radial velocity members, and including binarity from like time series of 10-year baseline. So stars that stay constant over those 10 years are probably not binaries, or not binaries in a sense that we should care about. But we estimate there are more than 1,000 members. And when you just do the Gaia membership analysis, then there are certainly more than 1,000 members. The metallicity is slightly subsolar, and what is quite interesting is the extinction. It's 500 parsecs away, but the extinction is basically 0 to what's this cluster, which makes it quite easy to work with it. And of course, we are able to confirm the age of 300 megayears with a bunch of isochrones. Down here, this deviation is not because of like that these stars are behaving weirdly. It's just because the color transformations are weird. Because once you go down here to the M dwarf regime, then we don't know really how to transform colors to effective temperature so that we can get the correct models. Of course, I also got the rotation periods from there. So this is the color period diagram for this cluster. And as I said, there was also calcium activity from a spectra. And so I did this, and then I plotted it against the, just against the color. So same axis as here. And again, this is the flux in the infrared triplet. And you can immediately see that this is basically a mirror image. So stars that are fast rotating are up here. Slower rotators are going diagonally over here. Of course, the color coding helps, but this is intended. So I can, just go from here to there. But as I showed you before, there's also this plot against Rossby number, so activity against the Rossby number, and this well-known correlation. So you can go from here to there quite easily. And I was thinking, well, if we can go from here to there, why not going from here to there to there? And we can do this. And all of these stars that you can see here with the cross had previously no rotation periods. So it looked like this, no rotation periods over here in this regime, for example. But if you fit a function to this, you can estimate a Rossby number and then go back to your light curves, use this Rossby number as a prior, and look in like a 10% range in the periodogram, which rotation period might be there, and then find these, which were previously just buried in noise. So that enables me to predict rotation periods, go back to the light curves, and basically doubled my yield, which is a pretty impressive thing. So for data that was already on my hard disk, just reanalyze this data and get like double the number of rotation periods. As you may have noticed, there is a scale change in here. So previously we went to like 20 days, now we're up to 35 days. So there are some pretty slowly rotating M dwarfs. Let's talk about them. These stars are also in the young open clusters, so in 2516 and the Pleiades over here, and now we have them in 3532. That means we can estimate how these stars are spinning down. And it turns out, if we assume that this sequence is the same as this sequence, then these stars are spinning down about the same as these normal slow rotators are doing. So they basically have the same principle in spin down, although they're already here in the M dwarf regime, which is pretty interesting. In particular, if you have a look at the field stars. So this is from the M-Earth project, rotation periods. So we have a bunch of fast rotating stars, so these are. And then you have a bunch of slow rotating stars corresponding to these. So it was previously thought that these are just old stars. So field stars up to 10 gigayears. But from this work, we can kind of say that there might be some stars that are initially slow rotators, just as for these high-MS stars, which is pretty interesting. So this is like an initial distribution of slow and fast rotators. Previously, it was thought that like all M stars are fast rotators. Okay, not all observations, there are also models. First of all, let's have a look at this kind of sequence here. So this is this transition sequence that I was talking about before, and all of these stars down here have evolved upwards. So they're rotating slower. There are no high MS stars here, so really all of them are now slow rotators. But when we put models on there, it doesn't look good. In particular over here, the data is here, the model is there for the same age. Shouldn't be. For the slow rotators, it looks somewhat better, but only like the latest model over here from 2020 is actually predicting our age correctly, or at least, or the other way around, the rotation periods at the given age. But it's not surprising that this model is predicting the correct rotation periods, because it was initialized at Pleiades age, and there was not that much happening in between, apart from like a small spin down. But the interesting thing about these like fast rotating stars here, we can estimate that the K0 star, so a star that has just arrived on the slow rotator sequence, is spinning down in about 80 megayears, which is pretty fast for a main sequence star. So it spins down from a period of like 1 day to a period of 5 days in this time. And you can see the models, well, do not really anticipate this. And we can also do like the other thing, that we have our observations, which is here in green, energy 2516. And then we evolve these stars, which are here in orange, just with one of these models. And as expected, the evolved stars are here, and the data is still up there. So we know that these models have to be updated. That's none of my business, but I can say we need updates. Okay, so let's summarize. Stellar rotation is a good age proxy for main sequence stars, because we have this age sequence. Young stars, young main sequence stars, can undergo the rapid transition from fast to slow rotation. Open clusters of common age have same rotation period distribution as we saw from Pleiades, Entity 2516, M50, and M35, and the Blanco 1. And there is this group of slowly rotating M dwarfs in young open clusters, which is kind of new. And if we combine activity measurements and rotation, so spectroscopy and photometry, we can get pretty nice synergy effects and double basically our yields of rotation periods. Thanks.
Thank you, Dario. Very clear talk. Are there any questions?
Yeah, thanks for your nice talk. Somewhere in the middle, I think you mentioned that the lower mass stars, or the cooler stars, had a wider range of rotation periods because they have deeper convection zones. I don't immediately see how that is linked. Could you explain a bit more?
So these stars have like larger range of spin down. So not like a larger range of rotation periods, but larger range of spin down at a given age. And well, I'm not an expert in the dynamos, but let's see if I can get it.
So it was a good question.
Yeah, well, it is a good question, but no, I actually can't tell you just on top of my head what the exact implication. But it has to be something to do with the deeper convection zones, because like the high-MS stars have very shallow convection zones, like F stars.
Any other feedback, comment, questions?
Hey, thanks for the talk. I wanted to ask, so in binary evolution, like magnetic braiding for some situations is very important. And like a very traditional model says that when you stop having a radiative core and just you have a convective star, so you have like no tachocline or anything, the dynamo dies out and it works differently. So is that total nonsense, or?
Well, we see that there is a continuum between fully convective stars and not fully convective stars. So there are similarities, but there's also research on that some aspects of the spin down are actually different in fully convective stars. So it's not totally nonsense.
Okay. So is the spin down expected more or less, these indications are that it's stronger, weaker? Does it go in any particular direction?
No, not really.
Okay.
But there are some effects, like there is a gap of rotation periods in the Kepler field. If you plot like all the rotation periods in the Kepler field, there is for like the high-MS stars, there's a gap which closes right at this beginning of the fully convective stars. So there was something going on that they're different.
Okay, thanks.
Thank you.
Thank you, Dario. I was wondering, can you elaborate on the saturation of activity level that you mentioned in the beginning? Like, why is that happening, or is it just not known?
Well, there are, of course, theories. It could be that the magnetic field is saturating, so that you cannot get more magnetic flux into at least the large-scale magnetic field. So on the small-scale magnetic field, there might be, you can maybe put in more flux and more, but on large-scale field, that's at some point maybe at this maximum. And then you also have like all the effects that depend on magnetic field are just saturating at this point. So this is one of the ideas.
Can you come back on the slides with the different clusters compared? You had different diagrams for the different clusters compared.
Yeah. Talking about this one?
No, with the different age showing, like, I think it's where you kind of demonstrate that spin down is a good age proxy.
Yeah.
By showing different clusters.
Yeah, these are different clusters.
Oh, okay. Okay, no, that's not the one that I thought, but okay. Let me
Later
look
or earlier in the talk?
Mm-hmm.
Later or earlier in the talk?
The 4 different quadrants.
Ah. You mean this one?
Yeah. Okay. So yeah. Maybe I don't really understand what's in there. So if you can.
So this one is that. So on black, you always have the distribution of NGC 2516, and then you have all of these other 4 clusters, and they have the same distribution. Because if you have like an older cluster, stars would be above, they've spun down, and a younger cluster, stars would be below here. So you can already immediately say, okay, all of these clusters have the same age, and like also these fast rotating stars over here, they have the same distribution. So this is like the ultimate test, getting different clusters of the same age and seeing, okay, you cannot tell one from the other.
Any more questions? And I'll reserve the last one for myself, actually. So you always speak about rotational period, but these stars...
We talk about periods, yeah.
So the stars, they rotate differentially. So how exactly do you determine, or how do you define a single rotation period number?
Well, there are two things to this. First, we can't observe a difference in rotation on these stars because we only see mostly one star spot, and that's at one latitude. So we take this, the rotation that we can observe from this star spot as our rotation period. But secondly, we think that these young stars do not rotate that strongly and differentially. They're more like solid in their upper photosphere. Of course, there are implications to the dynamo, but there are things to solve it.
Okay, thank you. If there are no more questions, then let's thank Dario again. Can we leave?
Curiosity, what's the dependence of rotational period for the sun with latitude? Does it vary significantly?
Yeah, it's between like 25 and 30 days.
25 and 30?
Yeah.
I mean, it's not that bad then, if you try to put a point in here. Okay.
Sure, but yeah, that's that's about the range.
Yeah. I can show you a nice plot. Okay, let's thank Dario. Thank you for coming.